So I'm going to talk about, the trust-based consensus protocol. So let's start the discussion. When we talk about, the distributed computing, we need coordination among different processes to agree on some sort of data values. For instance, if we talk about consensus applications, the processes need to agree on what transaction to commit and commit to a database and in which order. So there are a number of relevant applications where consensus is required. There are different types of distributed applications. For instance, page rank, control of automated vehicles, such as unmanned aerial vehicles, load balancing, and these kind of other distributed applications where we need some sort of consensus mechanism. So one of the key application areas is blockchain, where consensus protocols are an integral component of the system. So in this talk, I'm going to discuss a specific genre of consensus protocol, namely trust-based consensus protocols, and more specifically, I'm going to talk about uh, a peer-to-peer energy trading system, which is powered by cross-layer trust-based consensus protocol. This is one of the recent collaborative work we have done, a collaboration between academia in UK and Australia. Right, so agenda, the specific agenda include, I'll start the discussion by exploring some background concepts related to consensus protocols, peer-to-peer energy trading, cross-layer model, and then we will jump onto the premise of a cross-layer trust-based consensus protocol for peer-to-peer energy trading using fuzzy logic. Right, so a consensus protocol. A consensus protocol prevents a single entity within the network from controlling a blockchain or distorting the truth of what should be recorded. Double spending, is an example of what could happen if one entity tries to take control of the entire network by creating its own version of the blockchain. So in our context, if you look at the diagram on this slide on the right hand side, you can perhaps observe that this on a typical blockchain based renewable energy system, uh, it can be observed that the key building blocks of this system include peers who are trading energy and then smart contract with embedded logic and a shared ledger having energy trade related transactions. On the other hand, in the conventional process, we involve public microgrid. However, the blockchain driven process execute trade deal through smart contracts. So this is conventionally we have blockchain based smart contract driven energy trading systems. Consensus protocol. I mean, as I'm sure most of you are aware that there are different types of consensus protocols such as proof of work, proof of stake, proof of elapsed time, Byzantine fault tolerant, and there are some other categories such as proof of authority, proof of capacity, proof of activity, and few others. So if you look at this diagram, you know, this table on this slide, the bottom row shows the trust model, the by default trust model in these different consensus protocol. So most of them are by default untrusted or semi-trusted. Uh, the traditional process involves in one of the genres of consensus protocol is a proof of trust where it primarily selects transaction validator based on the service participants trust value. So we can actually embed the trust layer in some of the consensus protocol, and the core idea in energy trading system is that what we are going to discuss today. We have actually embedded the cross layer trust management system uh, to enable energy trading system. Right, peer-to-peer energy trading. As briefly discussed, peer-to-peer energy trading enables people to buy and sell energy to each other directly without the involvement of an intermediary. So, such a platform can be powered by blockchain, obviously, based on its characteristics, distributed uh, nature of the network, and a reliable P2P peer-to-peer trading system can be established, like many other marketplace systems. So, what is the control? What is the cross-layer model? Cross-layer design refers to sharing information among layers for efficient use of network resources and achieving high adaptivity based on the real-time information coming from the different layers of the system. So in a typical cross-layer design, each layer is characterized by some key parameters. The parameters are passed on to the other layers to help them determine the best course of action with regards to the current status. And we have used this cross-layer information for trust formulation and other purposes in our proposed energy trading system. Right, so let's move to the main agenda item. What problem we have attempted to solve here? Lack of trust, prosumers, that is both consumers and producers. Um, uh, Neither a producer nor a consumer of the electricity can be taken as a trustworthy um, entity. Therefore, trust establishment is a key requirement. The existing blockchain driven solutions mainly focus on the reputation based consensus or system architecture for trust establishment. The underlying mechanisms have primarily considered the behavior of minor nodes in the system and the opinion of the producers and consumers are not considered in the trust establishment evaluation processes in the state of the art studies. So these studies have considered trust constituent factors only at blockchain consensus or application layers and completely overlooked several important aspects that could be utilized for trust establishment and then ultimately evaluation purposes. So there is a lack of reward punishment mechanism in the holistic solution. What could be the potential solution to address this problem? We propose a cross-layer trust-induced consensus protocol and architecture to realize a blockchain-powered P2P energy trading system. Our proposed protocol, consensus protocol, rewards honest and punishes dishonest nodes in the network. So leveraging the human in the loop factor to compute trust. So to realize this concept in novel way, we particularly explored factors such as rating of traders from humans experience point of view, time spent by a trader in the network, total coins related, and trust score of the trading platform on the basis of both human and service experiences. Right. So let's have a more detailed uh, look at our proposed solution. Uh, we have four layers, namely network, consensus, application, and meta application layers in our architecture, as you can observe on the left hand side on this slide. The key functionalities include, some of the key functionalities in blockchain include mining, maintaining cryptocurrency ledger, consensus mechanism, collecting transaction, and block propagation. Those are grouped in different layers, in those different layers that I have just mentioned. We have used the concept of stable coin, trust coin. In that, trust coin can be pegged to the respective fiat currency of the country in which we intend to deploy the system. The buyers, sellers, and validator scores contribute to the application layer in the calculation of the trust coin, and the values of the upper and lower layers they contribute to the application layer. So effectively, different layers are talking to each other in order to carry out different functionalities related to blockchain and obviously related to trust establishment and evaluation. Information quality, ease of dealing, transaction safety, peak cost, non-peak cost, and satisfaction realized. These are some of the factors those realize human experience at meta application layer. And these factors have direct impact on the computation of trust score, which is then utilized to choose validators in the consensus layers. So basically, trust of all buyers, sellers, and validators are computed. Right, so let's have a look at the functionality of all those layers, individual layers. We start our discussion from meta application layer. Uh, in the context of our application, different entities, uh, those are sellers and buyers, would participate at this layer using the marketplace. So these entities would utilize a web-based user interface to create a wallet so as to simulate their digital identities by creating a private public key pair. An entity can access the marketplace using the user interface to buy and sell electricity. Our system has two types of transactions: coin transactions and trust transactions. Once a buyer accepts an offer, a coin transaction is created in which a certain amount of trust coin from the buyer to the seller is transferred. This transaction is propagated in the network, which is then included in a block. Once this block is added in the blockchain, implying the finality of the coin transaction, the buyer and seller belonging to the respective transaction will need to rate each other as well as the system. That is basically the marketplace platform. So they also need to rate their experience of the received service. All these form the basis for a trust transaction, which, similar to a coin transaction, is propagated within the network and consequently added in a blockchain and then to the added in a block and then to the blockchain. So once this happens, the respective trust scores of the buyer and the seller as well as the platform are updated using the process that executes at the next layer, that is application layer. Right, so the energy trading is rated at the meta application layer against a number of evaluation factors. We have named them alpha, beta, gamma, delta, epsilon. These are rating of the trader, total time spent by a trader, total coins traded, human experience, service experience. It is important to observe that the trust score of trader is derived from alpha, beta, gamma. On the other hand, trust score for the platform depends on delta and epsilon uh, factors. So trust values are shown as fuzzy numbers, namely high, moderate, and low, and can be derived from trust membership function as shown in this slide. I'm not going to discuss the details of this membership function. This is a standard function and it can be adopted as per the requirements of user application. Right, so next layer is application layer. Um, the value of trust is derived on the basis of trust coin. As I mentioned before, the smart contracts maintains the trust score for individual trader and validator in the system. The trust coin computation model intends to reward honest behavior of the validators, and the trust coin attributes include block reward, trust fee, trust score of buyer, and total coin transacted. So these are four attributes that are part of the trust coin. Consensus layer. Next is the consensus layer, the core layer. The proposed consensus algorithm is based on the concepts of proof of stake and proof of burn. So within this consensus layer, a node can be a validator after satisfying two conditions. First, it must stake a certain amount of unrecoverable trust coin in the smart contract. And then its trust score is above a minimal threshold value. that threshold value can be set by the can be agreed among the uh, relevant entities, and the trust score given by other validators. That is, once a block is added by a selected validator, the block is propagated in the network, which must be validated by other validators in the system. So the validator trust score is used to filter out the untrusted or less trusted validator out of the consensus process. So if a validator is found to act maliciously, uh, then it is penalized using defined penalty equation, which we have defined here. So these are some of the core building blocks of our proposal. Uh, we we evaluated performance of our proposal uh, by building an experiment setup on SimBlock simulator, and we specifically measured performance in terms of elapsed time, memory, and CPU usage of each round. So the elapsed time, if you look at the diagram, the graph, the uh, top graph on the left hand side, uh, you can observe you can observe that the elapsed time starts to increase as the number of node increases. The rate of increase of the elapsed time is almost exponential for proof of work and proof of stake. For our algorithms, it can be observed that the rate of increase is not as exponential as it is for proof of work and proof of stake algorithms. So similarly, in the case of memory consumption, it can be observed from the graph, even though the relative memory consumption is mostly similar, our consensus algorithm consumes the lowest memory among all algorithms, with proof of work consuming the highest in all node ranges. Uh, we also studied the evolution of trust score for different validators. The result of this experiment with three validators is plotted in this graph, where the trust score for each validator is updated after every 5 blocks. So if a validator misbehaves, for instance, validator 1 in block number 45, as it can be observed from this graph, and validator 2 in block number 30 and 50, its trust score is reduced drastically. Uh, so trust value has an important impact in the overall functionality of this energy trading system. The more trusted a party would be, the more uh, the more important role in the trading they would have. Right. So this is a list of some of the other ongoing or recent works which we are doing. Um, Fuzzy in the loop driven low cost and secure biometric user access to server. This work has recently appeared in IEEE transactional reliability. This is again, uh, uh, this work is done in collaboration with uh, academics from Australia, Canada, UK, and Turkey. Uh, Privacy preserved ranking of industrial sensing service. So this is one of the ongoing work which we are doing related to smart cities, where we have a number of services, automated services. Those could be discovered and ranked based on certain mechanisms. We are also working on AI driven aquaponic systems here, and some socio-technical business risk and vulnerability assessment processes for industrial control systems. And in relation to blockchain technology, we are working on some uh, healthcare and unmanned aerial vehicle solutions.